In this video, we'll learn how to actually learn a decision tree from a training set. The machine learning problem is that we'll have to decide if a person should or should not play tennis on a specific day. As you can see, we have 4 attributes: outlook, temperature, humidity, and wind that will be affecting our decision. We have 14 examples, and the decision column contains the results as to the decision that will be made according to the values of these 4 attributes. As we already know, in order to learn the decision tree, we'll have to find out the best attribute uh, as to uh, which we will be using as the root node of the decision tree. In order to do that, we'll have to find out the information gain of the decision with respect to each of the attributes that we have in the training dataset. So for example, first of all, we can find out the information gain on decision if we split on outlook. Next, we'll have to find out information gain on decision if we split on temperature, and so on. And the highest value that we get will be chosen as the attribute to split on in the root node. So let's first calculate the information gain due to wind, due to the attribute wind. As we know, information gain is just the reduction in entropy. So how we calculate that is by subtracting the expected entropy of wind from the entropy of the decision column, right? We already are familiar with the formula of entropy, which is stated here. So using that, we can easily find out the value for entropy of decision. In order to do that, we'll just have to count that number, the probability of each type of values in the decision column. We can see in the decision column that there are only 2 types of values, no and yes. So we count each of those values. We can see that there are 5 no values and therefore 9 yes values. So Pi for yes will be 9 and Pi for no will be 5, right? Sorry, Pi for yes will be 9 by 14 and Pi for yes Pi for no will be 5 by 14. So we plug in the values and get the entropy of decision. Now we just find the expected entropy of the wind attribute. If we extend this, we can write it as the following. For each of the values of wind, that is weak and strong, because wind has only 2 values in the training set, weak and strong. So if we extend it, then this will just be probability of wind equals weak times entropy of decision given wind equals weak, plus, due to this summation sign, plus probability of wind equals strong times the entropy of decision given wind equals to strong. Now let's first look at how we can find the entropy of decision given wind equals to weak. In order to do that, we can visualize the training set for only examples where wind is equals to weak, right? And just find the entropy for it. We can see that there are, for wind equals weak, there are only 2 no values, these 2, and all the rest 6 values are yes. So using the entropy formula, we can again easily find out the entropy of the decision. So this part is for decision equals to no, and this part is for decision equals to yes, right? And if you remember, the entropy formula was Pi log Pi, right? So here 2 by 8 is Pi for the decision no, and 6 by 8 is the Pi for decision yes. We can see that we get an entropy value of 0.811 for wind equals to weak. On the other hand, for wind equals strong, we can again visualize this reduced training set where all the examples are for wind equals to strong. Here we find out that there are 3 no values out of total 6 examples. So Pi for no is 3 by 6. And again, there are 3 yes values for wind equals strong out of the 6 examples. So Pi for yes will also be 3 by 6. So again, using the entropy formula, we can find out the entropy of decision given that wind equals strong. And we see that we get a value of 1 here. Finally, after finding out all the values of the small components, we can plug in all the calculated values in the main gain equation here. So we had earlier found out that h of decision was 0.940, and the expected entropy, for the expected entropy we had written out the formula elaborately as in equation 3. Equation 3 was the expected entropy equation, and we found out for equation 3 the entropy of decision given wind equals weak and entropy of decision for wind equals strong. The respective values were 0.811 and 1, right? And from the training set, we can easily find out the probability of wind equals weak because there are only 8 instances out of 14 where wind is equals to weak. So we plug that in here as well. And correspondingly, we can also find out the probability for wind equals strong from the training set because there are only 6 examples out of 14 in the training set where wind is equals to strong. So we plug that in here as well. So now with all the calculated values, we can calculate the gain of decision with respect to wind, which is 0.048. Similarly, we also find out the gain of decision due to the outlook attribute, the temperature attribute, and the humidity attribute, and find out the gain values for each of them. We can observe that out of the 4 attributes, the information gain for outlook is the highest, which is 0.246. So that's why we decide to set the outlook attribute as the root node and split on it at the first level. After the first split, our decision tree stands like this, where outlook is the non-leaf node and the 3 branches are the corresponding 3 values for the outlook attribute, which are sunny, overcast, and rain. Next up, we observe that if the outlook value is overcast, all the decisions are actually yes. So there are no values if outlook is equals to overcast. So what we can do is basically set the leaf node for overcast to be yes. That is, if the weather is overcast, the person will definitely decide to play tennis on that day. It doesn't matter what the temperature or humidity or the wind condition is.